because I have to cool down the batteries. For the spin? Yes, that way. Yes.
That way?
Yes. Yeah. And then this one, if you're gonna move, just on your.
Yeah, it can stay here now.
And then you might have said yes. Maybe it was. But that's you both.
Just have to stop the screen sharing again because I have to readjust the screens. Okay. That was not a good idea. Um, just need to oh, Screen share. Shouldn't matter now. I can use any of them. Yeah, because
Okay.
yeah, sure. In theory. Let me check. Yeah.
Yes. Everything you see. Perfect.
Yeah. Okay, cool. Well, then welcome back after the coffee break. The idea is now that we have a look into how to, or see how we can apply the methods that we have just seen in theory, how we can apply them in practice. I don't know if you have seen the material already. It's on my GitHub repository, OpenGeoHub 2022. And the slides from the lecture are located here in the slides folder. And what you need is the RMD file from the practice folder. And this is what I also opened here in R. And I would like to guide you through this tutorial where we will start with having a look on simple model predictions for spatial mapping and then discuss different cross-validation strategies, see how variable selection can be used, and then estimate the area of applicability. And just stop if something is too fast or if you have question in between. Okay, so I would start with loading the relevant packages. We need virtual species because this is a package that we use to produce our prediction task or simulate our prediction task with. We need a carrot because we use that for the model training. Cast is a package that has the area of applicability and the cross-validation strategy implemented, and then the rest we don't need to mention at that point. I set a seed here to produce exactly the same results. As you can see, 2, 3, 4, 5 is maybe some arbitrary number. Of course, I tested some seeds and looked for an example that produces patterns that are nice to visualize the things, but you can play around with that later on and produce different prediction situations. But I think the purpose of such a tutorial is that you also highlight certain patterns. That's why on purpose I chose something here where I looked at and thought, yeah, that's suitable to highlight what I want to show. What we do next is to simulate our data sets that we want to use. And we first define here our study area. That is on default here, Europe. You can also play around with that and change that to other locations later on. If you want to explore how that works, maybe for global studies, then just change the coordinates here. For this example, I want to use 300 sampling points that are clustered around 10 locations with a maximum distance of 150,000 meters around each of the cluster centers. So 150 kilometers around it. We will visualize that later on. So this is everything that I define up here, but you can also play around with that to produce other examples here. What we do next is to define the predictors that we want to use, and we are going to download bioclimatic variables later on. And what I'm going to do here is to define which of the bioclimatic variables we want to use for predictions. This is also something that you can change if you want to try others. I just selected some of the set of bioclimatic variables. I don't know, are you aware what bioclimatic variables are about this data set? So this is a data set that is based on a WorldClim data set and is giving long-term means for variables like, I don't know what is included there, warmest temperature of the summer period or precipitation in the wettest months and so on, to different variables that describe climate that might be relevant for species occurrences or for other ecological variables, because the prediction task that we want to discuss, as I will say later on, is an example of a virtual species distribution, and we might assume that climate variables are quite relevant to describe or to explain the occurrence of species. That's why we use them here as predictors. And it's a nice data set for Europe-wide studies and to test different things on a larger scale. That's why we're going to use it here. But yeah, we don't need to go into too much detail here about this data set because we want to put special attention later on how we do our model training. Simulate response is also a subset here of the bioclimatic variables. This defines the variables that are used to create the response variable. I don't want to go into detail how exactly the response variable is created. That's part of the virtual species package. But what you just need to know at that point is that these variables, so these bioclimatic variables here, are used to simulate a virtual response variable that you will see later on. And the same applies to mean PCA and standard deviation of the PCA. So these are also parameters that we need to create our response variable, as you will see later on. So this is just for now setting the parameters that we need and that you can change if you want to produce different examples. What we do next is that we download the bioclimatic data. As you see, I'm still using the raster package, so it's high on my list to do the transition sometime very soon, but please don't complain for that tutorial if you're still going to use that here. So the raster package has a nice function, get data, where you can download different data sets. For example, the bioclimatic variables from the WorldClim data set. I download them here in 10 degrees resolution. I hope that's going to work. Otherwise, I still have them on my laptop. Oh. Yeah, seems to work. Okay, and then when you see what we just did is that we downloaded raster data, so all the predictors or all the bioclimatic variables that are available here as a raster stack. And from them, I'm now only going to select those that we want to use as predictors, so those that are defined up here. The simple reason is that I want to reduce the size of the data set so that everything runs a bit faster later on. And next, I'm going to crop them to the extent of Europe, because if I just plot one of the bioclimatic variables that we just downloaded, so predictors, I just take the first one. You see that it's a global data set here, and we just defined our study area as the area around Europe. So I'm going to crop it here to the extent that we just defined in our list of parameters. If I then plot them again, and now because it's a smaller area, we can also try to plot all of them, or maybe not. Yeah, now we see them here, that we have the different bioclimatic variables as raster layers. So these will be our predictors. And in addition, I'm creating a mask for land area, so to define the area for which we want to make predictions, because later, so you know, we can technically apply our model everywhere, even for oceans if we have values there. And because we want to limit everything to land areas, I produce a land mask here. I can also plot it. I think it takes a few seconds. Yeah, so we just have a polygon for the land area. So this is our study area for which we want to make predictions later on. What we do next is to generate our virtual response variable. And as said, I don't want to go too much into detail how we do that. Let's just accept it as it is for now. We can also plot it. So this is our response variable. This is what we want to reproduce later on, because this is what we assume is our truth. it's simulated, of course, but this is what we want to produce later on with our prediction model. So based on the training data that we have, we want to create a prediction model to make predictions about this virtual response variable here for the entire area of Europe. And a good prediction model would produce something that looks exactly like that. So if we get something exactly like that later on based on our field samples, on a model that we trained based on the field samples, then we produced a good prediction model here. Okay. Then to simulate a typical prediction task, we're going to simulate our reference data because, as said, we usually start with having our local field observations as reference data for model training and validation. That's why we're also producing something like that here. And as said, we're going to do it in a clustered way to highlight the patterns or the problems that we might have when we have limited and clustered data sets. So for the entire land area, we now develop or now we create our 300 sampling points that are located around 10 clusters in a certain distance here. And then we can also visualize our data set. So we have here again our response variable, quite small, our response variable, and overlaid on that we have our training location. So you see that we have highly clustered data that might be a bit exaggerated compared to real world prediction tasks. But as said, we want to highlight certain patterns. That's why we keep it like that now. So we randomly selected 10 clusters now, and around them we sampled our training locations. Oh, there's no zoom there. This is what I want to close. Yeah. Okay. What we're going to do next is to prepare our training data set. So we actually already kind of have our data set. We have our predictors. We have our response locations. Now we're just going to combine them into a data frame to have everything available for model training. So we're going to extract our predictor values at the location of our sampling points. And we're going to do the same with the response variable. So also there we're going to extract our virtual response variable at the location of our sampling points so that we get a data frame here where we have for each of our sampling locations the different bioclimatic information that we use as predictors. And in our last column here, we have the response variable. So this is our training data set. And the idea is now that we want to train a model that is able to predict this response variable based on this set of predictor values. And we could now start with already talking about cross-validation, but I thought that we're not going to do that. But before we do these details or before we talk about these more complicated things, I think it's always quite nice thing to just first create a first map and see how it looks like, and to see that this is actually technically something very easy to do, to train a random forest or other machine learning model to make spatial predictions. So without that we discuss that any further, let's just train a simple model without caring about cross-validation, variable selection, and so on. So let's take the naive approach and just throw our predictors and our response variable into a random forest. And we can do that with caret by using the train function. We put in from our training data set our predictors and the column that includes our response variable, and with method rf we can specify that we want to train a random forest, and that's it. So 3 lines of code to run a model or to train a model. And then we can inspect our model outcome. It takes a few seconds to train. maybe a bit more than a few seconds. Yeah, so, oh, that's new. I definitely never had that at that point. Interesting. Okay, again. Maybe I just reduce the number of trees to make it a bit faster. Is it running for you? Yeah.
And how was the response variable removed?
Don't ask that question. I don't quite. So it's based on principal component analysis of the bioclimatic variables that we use to simulate the response. So here the set of I don't know which ones here. Those ones that we chose here, and yeah, it's somehow derived from the response based on the principal components with different parameters, but you would really need to look into the virtual species package. Okay, back to the model. Hopefully now it works. Yeah, okay. Okay, so this is the model output that we get. So we get here the summary that we trained a random forest on 300 samples with 13 predictor variables. And we get the following results here. So R squared 0.96, 0.96, and 94, depending on the tuning parameters, because per default, 3 different values for the tuning values are tested here for the random forest model. The mtry value is one of the tuning parameters. So when we look at that 0.96, that already sounds like a suspicious number. Jakob just said everything above the 0.95 number should be regarded as a suspicious value. So this is what we definitely have to talk about later on during cross-validation, because what you have to keep in mind at that point is that this number here, or this performance, was estimated based on bootstrapping, where randomly samples were taken to or held back to test the performance. So this is actually that comes close to the results that we will get when we do a random cross-validation. We will explicitly do that in a few moments, because actually I first thought about not discussing that at that point, because we wanted to produce our nice map to start with. So what we're going to do is that we feed this model into the predict function that is taking the predictor stack, so our entire set of predictor variables, and takes the model as a second argument. And if we do that and just plot it, we get our first prediction. So you see, technically, it's really no problem at all. You have your reference data, you have the predictor variables, you create a nice data frame that contains all the relevant information. It's 3 lines of code to train a model, and it's 1 line of code to make the prediction, to produce here a Europe-wide map of our virtual response variable. Okay, so technically no problem. And you remember the lecture earlier on started with the question, how good is our prediction, or how good is the map that we just created? And this is a point where we now want to talk about the different cross-validation strategies. So the idea is that we're now going to compare a random cross-validation with a well, I just call it spatial cross-validation, although I said earlier on that we should, or I think we should not just call it spatial cross-validation, because there is not the one spatial cross-validation, but it always depends on how we define our folds. But what we're going to use here is I call it leaf cluster out cross-validation. So we divide our training data into 10 folds, where in each fold we leave one of the spatial clusters out. So if I go back to this figure here, so I have here my clusters, and in the first iteration, maybe all data from this cluster will be held back. and will be used to test the performance and so on and so on. So it's a 10-fold cross-validation, but in each iteration, one of the cluster or all data from one cluster will be held back for model validation. Okay, so let's start with getting the random cross-validation defined. So for random cross-validation, we can divide our data set into 10 random folds. We could also change that number here with the function create folds from the caret package. And then we get here our 10 folds, how we divide our data into the 10 folds. And we can start our leaf cluster out cross-validation with the function create spacetime folds from the cast package that is actually not doing much here. It's just taking the sampling points and the information to which of the clusters each of the training data belongs, and then it's dividing them into n cluster folds. So it's only it's only used to split the data into folds by their cluster ID. So nothing else happens here. And when we do that, we see here again which data are used for training in this index part and which ones are left out in this index out part during each iteration of the cross-validation. So we have here 10 vectors of data that are used for training and 10 for validation. And in each of the data set. So here in the first one, for example, the first data point is not used for training, but we see here that it's used for validation. So this is the information that we get when we print this spatial cross-validation output. And as a third cross-validation strategy, we're going to try the new nearest neighbor distance matching cross-validation that takes, again, our sampling points, and it takes the study area, because this is the area for which this function is then trying to match the nearest neighbor distance distributions. That's why it needs the information for which area we want to make predictions. And then if you do that, that takes a few seconds. Yeah. But that's in a cast package. Yeah. So in theory, it should be available in the most recent version on CRAN. So I made a update of the version just 3 or 4 days before the summer school.
No, it's just saying that could not find function.
And NDM, but do you have cast installed and the library loaded? And then the relevant question, which version of cast? Because it should be 0.7. It was not included in the previous versions. What about the others? Can you? Good. Yeah, good. Okay, great. So the information that we get here when we print the NNDM object is that, again, we have 300 data points, that's not a surprise. And on average, we use 262.58, let's ignore that, 262 data points for model trainings. So this indicates that, not all data points are used for model training, but some are excluded in order to match these distributions here. Okay, now the next thing that we want to do is to explore which of the cross-validation strategies are most appropriate for our prediction model. And therefore, we're going to compare the nearest neighbor distance distribution with using the different cross-validation strategies. And let's maybe start with a random cross-validation. We have in cast a function for that called plot geodist, where we feed in our sample points. We feed in our cross-validation folds, and the model domain, so the area for which we want to make predictions. And I here say show plot equals false because I'm going to plot them all together later on. So we can do that for the random, for the spatial, and for the NNDM cross-validation. And then, yeah, this function allows us to compare these distributions. So we have here first the results for the random cross-validation, and we see exactly the same pattern as we just discussed during the lecture. So we produce here prediction situations during cross-validation. That's what you see in blue, that are comparable to the training data, which are located here under this curve, so the red distribution. But it's not representative for our study area because prediction requires that we apply our model later on to make predictions for areas that are far away from our reference data. So this is what this figure shows here. And we can now do the same for the spatial clusters. And this now looks much better. So the cross-validation situations that we create, which are again shown here in blue, are quite comparable to our prediction tasks. So we never compare or we never create prediction situations for areas that are nearby our samples. So it starts here around this part, but in general, that looks quite close to what is required during prediction, which is good news because I'm going to use that later on for variable selection, because with the leave one out cross-validation, it would take quite a while. But this is what I said earlier on with a kind of trial and error approach. So we can try to match these distributions by trying to adjust our spatial folds in a way so that yeah, we can see that the cross-validation situations or the prediction situations that we create during cross-validation are representative for our prediction area. And as a third example, now we see the nearest neighbor distance matching approach. And here you see that yeah, the situations that we create really quite nicely fit to what is required during prediction. So they're nearly identical, not quite, but nearly identical, which means that yeah, we're testing during cross-validation situations that are comparable to what is required when we produce our Europe-wide map. Okay, so this just shows us now how representative these samples are for the entire area. But now the question is, what is the effect of the different cross-validation strategy on the performance assessment? So what difference does it make whether I use random or spatial, so spatial leaf cluster out, or the nearest neighbor distance matching approach to assess the performance of our model? So we have just seen we produced our Europe-wide map of our virtual response variable. That was one line of code. And now the question is, how good is that? So how good is that map? And therefore we train the models here with our three different approaches. So in the first approach, we train it with random cross-validation. I do that by just specifying here that I do a cross-validation on default. It's doing that in a random way. In my second example, I feed in the spatial folds that I created earlier on, so that it makes sure that in each iteration it leaves exactly these spatial clusters out. And in a third example here, I feed in my nearest neighbor distance folds. Short question, why do I need index and index out for the nearest neighbor distance matching cross-validation? Why do I need to specify both during model training? Because for the others, I just said index. So these are the data points that I use in each iteration for model training. For example, in the tens fold, it's the idea of these data points here, but I never said which ones I'm not using. So which ones are used for validation? I only specified those that I use for model training. So why do I have to specify both for NNDM? Maybe it helps if I say that automatically the data that are not indicated here as training data are automatically used as test data. Yeah. Yeah. So you're talking about the spatial leaf cluster out approach? Yeah, for this one, so you're right. So those that I use for training, I'm not using them for testing, but it's exactly the opposite of the training data. So those data that are not part of this training data set here are automatically the testing data. Yeah. Yeah. Yeah, exactly. So I have to exclude some data points. So in each iteration, some data points are completely excluded. They're never, or they're not part of the training data set, and they're also not part of the test set. So that's why I have to specify both, so index and index out, because index out is not the opposite of index here, because some are just excluded. And apart from that, the model that I train here is exactly, or kind of exactly the same as I did for the simple example that we have seen in the beginning, except for that I also say that I want to get the importance of our variables later on. And I reduced the tuning here to make things faster, but apart from that, it's still the very simple approach here of model training. Did I run them already? I don't remember. Do it again. Okay, and now we can compare the estimated performance. So let's start with a random cross-validation. Again, 0.96 according to Jakob. That's a sign for suspicious model. So we should probably better not trust that value, which makes sense if you look back into here the distribution plots where we've seen it with a random cross-validation. We're not testing the ability of the model to make spatial predictions. So it's not surprising that the performance is very high, because we were just testing how well the model is able to make predictions for new data points that are located in the same cluster. And we were never testing how well we can make predictions for completely new areas. Okay, let's have a look at the spatial leaf cluster out cross-validation 0.81. So that looks at least, or that looks much more reliable. And when we look at the nearest neighbor distance matching, we don't get an R squared because it's not implemented in that way. So probably we should better compare root mean square error values. So here we have 0.07. With the spatial, we had slightly higher 0.1, and with the random, we got 0.04. So this was very low error, while for the spatial validation strategies, we got higher error estimates based on our cross-validation. So now we have an advantage with our prediction task, because we simulated the prediction task, which means that we have a spatial continuous reference map. So when we just look here at the cross-validation results, this is just an estimate about the model performance, but we don't know if this is really representative for the true map accuracy. We discussed which one might be reliable, which one might not, by looking at these plots here. But at the moment, we don't know, but we can double check, because we're in the lucky situation that we have a continuous reference, which we, of course, usually don't have in real life. But here we can do that. So we can, we made predictions already. So we can calculate the true difference between prediction and response, and also plot it here. So what we see in this plot is again here the prediction, and we see the true absolute error. So we see here the pattern that we have already discussed in the presentation that we have here in Norway and also in the Alps, very high error. So here the true reference was very different from the predictions that we have made based on a forest, on a random forest. And we can also calculate the root mean square error for the entire area, which is 0.11. So quite comparable to what we estimated with our spatial cross-validation approaches, compared to 0.04 that we got with a random cross-validation approach. So apparently our cross-validation strategies, so the spatial one and the NNDM, were quite close to the true map accuracy here, while the random cross-validation error was quite considerably overestimating the performance. Okay, we talked about in the lecture that changing here the cross-validation strategy without using that for model tuning is only changing the estimated performance, but it's not changing the predictions. We want to see in the following if we can use the cross-validation to also improve our model by selecting only variables that are relevant for spatial prediction. So in this way, we can exclude all variables that are either counterproductive or just not relevant. So the idea is that we feed all of our potential predictors into a forward feature selection. It looks exactly like model training, but it's a wrapper around the model training. So in this variable selection, the different combinations of variables are tested. So it starts with all combinations of 2 predictor variables, is testing the performance by using the selected cross-validation strategy here. And then based on the 2 best performing variables, the number of variables is increased. And the variable selection stops when none of the remaining variables could increase the prediction performance. So that we can exclude all variables that are not suitable for spatial mapping. The forward feature selection takes a while. That's why I also decided to use here the spatial leaf cluster out cross-validation and not the nearest neighbor distance matching, because 10-fold or 300 folds make a difference. Although if I had the time now, I would use an NDM approach here for variable selection as well. Yeah, and now it takes a while because it's just testing for the different combinations of variables, the performance based on our cross-validation. Shouldn't take too long, maybe another few seconds. Yep.
In the lecture earlier, you talked about for each pixel calculating the distance to the nearest, once we get like the average distance that you're extrapolating. Where is that in the code? Because I don't see where you're dealing with like inputting the raster and getting.
Yeah, not yet. So here we're so far only looking at geographic distance.
Okay.
Or what do you mean? So
I thought,
for the decimal. Yeah, we come to that.
After the neighbor distance and
Yeah.
how do you know the distribution is going to map between your neighbor, like for cross validation and like the distance you actually need to extrapolate?
Yeah, you can do that already now, but the idea is that we use the trained model to weight the variables so that we can so that those variables that have the highest importance in the model are also weighted or weighted differently compared to those that are not relevant. But you can also calculate the distance. Now I can later show you how that works. So you don't have to train a model before you do that. But I'm going to do that now so that I can get the weights for the variables. Okay, variable selection is ready. It says it could not increase the performance when using more than 6 variables. So apparently it decreased our 12 variables to 6. We get an root mean square error of 0.07, so we could slightly increase it compared to the previous model, and we can now also plot the results of our variable selection. So what we see here in red are the different model runs that use two variables. We have a highest standard deviation here because or some of the models just produced good results, some produced completely bad results here. And the idea is then that based on the best performing two variables, so it's these two, or these two here, the number of variables is increased. So these two variables are used. I'll show you which ones these are later on. Then a third variable is tested, a fourth, a fifth, and so on. And here with the seventh variable, you see that the root mean square error is increasing. So none of the remaining variables could increase the spatial performance of our model. That's why it stops there and says, okay, I'm not going to use any further variables. You can also inspect which variables are selected either by just looking at model forward feature $selected variables. So these are the bioclimatic variables that are used. The others are removed. You can also plot it by saying type is selected, I think. No, it was something similar. Plot type. Okay. Yeah. So now we see that the best two performing variables were the bioclimatic variable 5 and 12, whatever that is. We would need to look that up now to interpret if that makes any sense or not. And based on that, we could increase the performance when we use bioclimatic variable 19 and so on and so on. So here you see which variables are then selected by the variable strategy. Okay, based on the selected variables, we're now going to train our final model that we want to use later on for prediction. So here I train a model again, but this time not with all predictor variables, but only with those that have been selected by the variable selection strategy. And then I can also use the nearest neighbor distance matching approach again to estimate the performance. So now we could decrease it to a estimated root mean square error of 0.05. And we can again check or compare with the true error, because now we really got another prediction because we selected or we reduced the numbers of predictors, and therefore we definitely also produced another prediction here. And with this prediction model, we could get down to a root mean square error of 0.08. So now we still have a bit of mismatch. So our NNDM approach said the root mean square error is 0.05. So that's root mean square error estimate, but the true map accuracy is 0.08 in this example here. But we might come back to that later when we discuss about the area of applicability, which we will now do in the following. Because you see, again, technically no problem, we can produce predictions for entire Europe. And the idea is now to limit predictions only to those parts of the study area where we enabled our model to learn about relationships. And this can be done with the function AOA for area of applicability. Unfortunately, it takes a while to run. There's also a tutorial in not that long. Okay, a tutorial in the package that explains a bit how to parallelize this approach. So what we see here now, before we look at the map, are the values for the dissimilarity index in blue that we produced during cross-validation, or that we created during cross-validation. And in red, we see what is required during prediction. And you see here is a dashed line, the threshold. So everything that is beyond that threshold is considered as being outside of the area of applicability. So everything with a dissimilarity value for the dissimilarity index above something like 0.5 7. Let's see. I think it's stored somewhere here. Threshold 0.667. So everything larger than this threshold will be considered as outside the area of applicability. We can now also plot it for entire Europe, area of applicability, or let's start with the dissimilarity index. Yeah, so these are the values for the dissimilarity index, and you already see that some locations have values above 1, above 2, and yeah, keep in mind our threshold is 0.67, so we already see that some areas will definitely be removed, and we can plot the area of applicability after applying the threshold, which then looks like that. So it only has 2 values, 1 and 0, or whatever you want to whatever values you want to give it. So you just have inside or outside the area of applicability. No. Yeah. Or at least it's not that that easy to make sense of these units. So we're still thinking about yeah, maybe I should so that you could at least normalize it with what you observed in the training data, so that you can interpret like everything that is greater than 1 means it's greater than what you observed in the training data. But so far it's really hard to really interpret these values. Oh. Okay, now we can also compare all the results that we've just created. So we have again our response variables, so the true response, we have our prediction, we have the true difference, and we have the dissimilarity index, where again we see that the patterns are quite similar. And we have here the area of applicability, where apparently, yeah, Norway, but also here in southern in the southern part of our study area, many areas are considered as being outside of the area of applicability, where it suggests that we should not make predictions for these areas, because we never enabled our model to learn about these predictor values that we find in these areas. So suggestion would be actually to mask the prediction and yeah, present predictions only for this area. And we can now also calculate the root mean square error just for the area of applicability, which is now 0.05. And if you remember, this is exactly what we got as an estimate from the NNDM approach, which makes sense because the definition of the area of applicability is that this is the area where we enabled the model to learn about relationships and where the cross-validation estimate holds. Yeah, if we now only focus on the area of applicability, we indeed get a map accuracy, or we have a map accuracy that is highly comparable to the estimate that we got with our cross-validation approach. Last thing I want to show before we can quickly have a look how to use this with MLR3 is that we can have a look how to use the dissimilarity index to get a quantitative idea about the prediction performance. And therefore, you see the function calibrate AOA with multi-CV equals true. In this case, different cross-validation strategies are performed in the background that create clusters in a predictor space, so that on purpose you create situations where you test extrapolation in predictor space, and you create situations where you test the performance for areas that have very comparable values to the training data to produce a large range of different DI values, and to test the performance by comparing the predictions with reference data. Because as said, the threshold here, again, it depends on the selected cross-validation strategy. If we had performed, or we could, or you could test that, because you have the random cross-validation as well. So you can test what area of applicability you would get if you apply the random cross-validation, and it would look very different. It would be limited just around the clusters used for training, but you would also see that you get an estimated performance of probably R squared above the suspicious threshold, which would then mean that yeah, this estimated performance is also only expected to be valid for the areas around these spatial clusters. Okay, so the results for this idea to use it as a quantitative measure are shown here. So you see that with increasing dissimilarity, the root mean square error increases. It flattens out after a certain value. And the idea is now that we use this model that you see here in the dashed line to map the estimated performance, which would look like that. So that you have here areas in yellow where you have high estimated root mean square error values, and the areas shown in blue are the areas that are likely very close to the training locations, and therefore we have, or we expect, very low error values here. And now then finally we can yeah, present this estimated performance here in color. There are still areas that are considered outside the area of applicability because we only estimate this relationship here, if I go back to this figure, up to the maximum dissimilarity index that we observed, because we don't know how this changes beyond that, because we never had a chance to create values for the dissimilarity index here that are greater than 1. And therefore, there are still areas that are outside the area of applicability where we don't have an idea about the prediction performance. That's why here in this map, yeah, you still see areas that are considered outside the area of applicability. Okay, this was the short insight into how to run these things in practice. The last part of this script was a first try to use NNDM and the area of applicability with MLR3. I think Patrick would need to help me to explain things here. I will just run it, and if you have questions, there's the expert for MLR3. So I load the required packages, although I think I could shorten that a bit. I don't know. And then I use again here my training data only with the variables that I selected with a forward feature selection as my training data set. My target variable is called response in this training data table. And then I'm going to train a random forest model on that task. And to prepare the cross-validation, I have to use here a custom resampling approach where I can then feed in the index values and the index out values or the index train and index test values that are created from the cast package. So you remember these are the data points that are used for training or used for testing in each iteration. And yeah, I can use them to do the cross-validation here. Just comment on that, Patrick, if you want to jump in.
To instantiate the resampling, just it's automatically do something call. It doesn't really do that.
This one here?
Yes. And
okay.
Usually I
oh, okay.
told people points that they try to use spatial temporal task instead of the normal task, but then of course depends on the coordinates. But here with them, particularly your application here, because it's doing something different and specific. And for the custom resampling strategy that you apply, so this is the one that I labeled as fully predefined in the morning. So she's just putting in already all the resampling instances and training test splits really predefined in this list. So maybe you can just also show them what it looked like, maybe what you put in. how the list looks like if you hang over.
Yeah.
It's just-
Yeah, because here the spatial or the coordinates were already considered in the NNDM function from cast. That's why we don't need to consider it here anymore in MLR3.
it's just a list.
Yeah.
It's set already, and it's something, so there's no moving positioning on this case. It's like the RSVP plus.
Okay. Then we can use a trained model to make predictions and plot the predictions, and I guess they look quite comparable.
Maybe
480.
because I see that quite a lot.
Oh.
This might be a bit confusing. There are two things, of course, you can do. Either you call the method function of the learner here to predict, or you wrap it into the S3 predict, right? And some people might be confused what actually is the difference and what's happening here. So an MLR3 learner has a train and a predict function. And when you call the predict method, then it's being written back into the object. Whereas if you do it like this, you create a new object prediction here, and you just access the learning model from the MLR3, but you don't use anything else. So actually, this is using generic predict function here on the predictors object, and on the quote unquote native model that we fit it into the model slot. And it depends a bit on which way you do it, but this way, so to say, it's just in the predict section here, not really using MLR3 internally, so to say, because it's just making use of the model that is stored in the slot. And a different way to write this would be to use the MLR3 predict method and then just get out the prediction and then store this in an object. So both would be doing the same thing, but just in different internal ways to create a prediction. Maybe this was still confusing. Our presentation. This is, I mean, I see why this is done like this. And the other way around as well, and why there is no way that we can prevent one or the other. And but yeah, that's enough comment on that.
But it produces the same predictions.
Huh?
It produces the same predictions.
Exactly.
Yeah.
That's a bit more.
Yeah. So if you're familiar with MLR3 now, or you're going to make yourself familiar with that, you can. So this tutorial is just intended, or this part of the tutorial is intended to show you that you can use the developments that we made here in a cast package also in MLR3. So you don't have to use Caret if you prefer MLR3. So you probably know better, or Patrick definitely would do it differently than I've done it here. But yeah, the main intention is to show you that you can use them with MLR3 as well. Okay, so you can also calculate the area of applicability. You have to take a little detour because you have to extract the relevant parts of the objects here. So you have to, so you can't feed in the model itself as we have done when we trained it with Caret, but you have to feed in the training data, the variables, the weights, okay, and the cross-validation folds all manually. But once you know where they're where you can find them, that shouldn't be too much of a problem because it's all either in the task or in the learner object here. And then we can also calculate the area of applicability. That should look quite comparable or kind of identical to what we have done when we used it with Caret, so quite similar here or identical. We can also estimate the root mean square error, which is also 0.05 is NNDM by using it in the MLR3 way. Okay, so that would was everything that I wanted to show. I also linked some further reading documents, scientific papers, and tutorials about these methods. I don't know how much time would we have. Tom said I'm allowed to stop earlier today.
Yeah.
Yeah, so last thing would be questions from your side, and otherwise I'm here until tomorrow morning, midday. So you still have time to ask questions later on. Is there anything you want to ask now? Yeah.
Thank you. It's a basic question, but what is better to compare, how to compare models with the R-square or with the Hanna?
Does anyone want to comment on that? Ben? Yeah, I sometimes so what's sometimes quite dangerous with the R-squared is that especially when you create prediction situations where you leave entire spatial units out and you just look at the R-squared value that you get from the data within one fold, and you have a very low variability of values there, then it's very hard to get a high R-squared. But when you compare it over the entire data set, it can quite nicely distinguish between high and low values. But if you only have quite similar values within one fold, it's hard to express that the model generally fits the data with the R-squared values. That's why I prefer to look at the root mean square error.
Also, more measures make it more complicated. So
Yeah.
the skill of model or something.
I mean, for classification, it would also be completely different.
One more question: if our data set has been long range, and the models are all well with the low values, doesn't do the job and it's no high values. In this case, the RNCs will indicate, or we can use other indices.
I'm not sure. Someone else? So I never experienced any.
So sometimes we have working with the source salinity. So most of the data have the low value. Even sample has the high value, and the models works with the well with the low values. I can explain correctly. So when we go into the high values, the models cannot predict well, but we are reporting at average. Yes,
There are other measures we can look into. And it's typical kind of zero inflation problem. So a lot of background noise, and somewhere something is happening. And particularly our models learn the kind of the typical stuff. Or they learn what's kind of most of the features have. And most of the features kind of really low values. Because they don't see those high values. And then you can tune them in a particular way, which you can find those experiences. And then you can use different functions to really kind of focus on these high values to set the model and say it's a good model because it uses this feature that I know is there, and I just kind of it's good average, which is kind of root square. So I don't have on the hand side. What is the direction you can search?
Okay, other questions? If not, then thank you very much for coming to this workshop.
No.
Yep.